remote to operate from there. Yeah. Good morning. Today we are going to learn about Raman spectroscopy. In the last session itself, I already explained to you what is Raman spectroscopy. Raman. So this is the scientist. You can see here. Sir is for respecting him. Actually, C.V. Raman. He is a Nobel laureate in 1931. Nobel laureate. His work is completely focused on scattering. Raman scattering. So, for example, if we have a molecule here, when the radiation incident on it, we know already about absorption, we know about emission, we know, but we don't know about scattering. This is the third phenomenon. We know that molecule is having absorption phenomena, emission phenomena, and also the third one is scattering phenomena. If you consider molecule as an opaque body, then it will start scattering radiation in all directions. Then he studied what is the wavelength of incident radiation frequency? What is the wavelength of incident radiation frequency? And what is the wavelength of scattered radiation frequency? And he found that scattered radiation frequency is different from incident radiation frequency. And he started recording scattered radiation, and he found a Raman phenomena that is called Raman scattering. And IR and Raman complemented to each other. These two techniques are complemented to each other. Actually, both of them are showing us vibrational frequencies. But in infrared spectroscopy, we are getting vibrational frequency directly. But here, we are getting vibrational frequency in terms of Raman shift. Raman frequency shift or Raman wavelength shift. So, IR frequency, that means IR vibrational frequency is equal to Raman scattering shift. So that's why the information what we are getting from IR spectroscopy and Raman spectroscopy is the same. But why we need Raman when we are having IR? Already we have IR. Then what is the need of having Raman? The thing is, in infrared spectroscopy, for example, so if we have a look in infrared spectroscopy, what we are measuring is IR vibrational frequencies. And for example, if we have H and H, this is called homonuclear diatomic molecule. And we have this is also same. So all these molecules are homonuclear diatomic molecules. That means same nucleus. It is same nucleus binding each other. In this case, no dipole moment change. That means there is no change in dipole moment. Why there is no change in dipole moment? Because these are two same atoms. For example, if you have HCl, here on chlorine we have chlorine is more electronegative than hydrogen. Okay, we have delta minus, this is delta positive. Because of these charges, when there are vibrations, the dipole moments keep on changing. Actually, interaction between radiation in infrared spectroscopy, the interaction between radiation and the vibrations is due to change in dipole moment. If there is no change in dipole moment, there is no IR peak. These bonds are IR inactive. IR inactive means they will not give any band in the IR spectrum. No band in the IR spectrum. So, but if you have HCl, there is band in IR spectrum. And I am going to show you also another a symmetric molecule like this. C double bond C, CH3. You can have a look here. In this molecule, this is symmetric molecule, and this is double bond. Actually, double bond is a functional group. We expect to get a peak at around 1630. There must be a peak, but because of symmetrical nature of the molecule, this is IR inactive. All the bonds which are IR inactive are Raman active. All the bonds which are Raman inactive are IR active. Raman inactive, IR active. If IR inactive, Raman active. That means if we have IR spectrum and Raman spectrum, you will not miss any bond. You will have the vibrational frequencies of all the bonds if you have both IR and Raman. So that's why we usually say that IR and Raman are complementary to each other. Now I am coming to theory of Raman spectroscopy. In the theory, we know that let me explain to you this way. Already we have seen atomic spectroscopy. Already you have idea. Okay. Even in the molecular spectroscopy, it will be the same. But this is not molecular spectroscopy. IR and Raman, both of them are molecular spectroscopy. Okay. For example, if we have like this E0, E1, these are molecular. Let us consider this is molecular energy level diagram. Molecular energy level diagram. E0, E1, sorry. This is E1. E0, E1, E2, E3, E4 and so on. Okay. Now in between we know that there are vibrational levels. In between electronic energy levels, there are vibrational levels. In between vibration levels, there are also rotational energy levels in the molecules. We know that. Okay. But Raman introduced another type of energy levels just below E1. He visualized another states called as virtual states. He introduced the concept of virtual states. Virtual states are completely different from vibrational as well as rotational, and these are also present in between electronic energy levels, but just below the first excited level. Just below. Okay? Just below the first excitation level, there are virtual states, and that is the concept. Now, here you can see there are virtual states. You can say this is V is equal to 0. These are energy levels corresponding to E0. Okay? Which energy levels? These are vibrational energy levels. This is not showing there. Okay. These are vibrational levels corresponding to E naught, and E1 will be somewhere here, and these are virtual states. Virtual states. Now, when you are considering, why it is not showing? It is not showing the writings there. Okay, maybe it is because of the projector. Right, anyhow. So, for example, a molecule is at V is equal to 0. V is equal to 0. Now, let us consider it is transformed to J is equal to 0. J is equal to 0. V is equal to 0 to J is equal to 0. Okay. Now, while coming back, let us consider it is stopped at V is equal to 1. Are you getting that? This is excitation to virtual state, and while coming back, it is stopped at V is equal to 1. Where it is started, V is equal to 0. But while coming back, it is stopped at V is equal to 1. So the excitation energy is different from scattered radiant energy. Yeah, excitation energy is different from scattered radiant energy. And how much it is different? This is the difference. Okay? What is this one? This is the difference in the vibrational levels. That means that's why we are getting also a frequency shift. In the Raman spectrum, we are getting frequency shift that is corresponding to difference in the vibrational energy levels. That's why IR frequencies are equal to Raman scattering shift, or we can say simply Raman shift. Raman shift. Okay? Right. Now we are coming to this one. This is one, and these lines which are having the scattered radiant energy, lower energy than excitation energy, that is called Stokes lines. Stokes line. You need to remember this one. Stokes line will have lower energy compared to excitation energy. Okay? Now I am coming to another situation. Let us consider the molecule is already present in V is equal to 1. And the molecule is shifted from V is equal to 1 to J is equal to 1. V is equal to 1 to J is equal to 1. And from J is equal to 1, when it is coming back, it is relaxing up to V is equal to 0. Are you getting the point? It is starting from V is equal to 0, but while coming back, so it is starting from V is equal to 1, but while coming back, it is relaxed up to V is equal to 0. That means the scattered energy is more than the excitation energy. Excitation is from here to here, but scattered is from here to here. This arrow is longer than this arrow. How much longer? The difference in the vibrational energy levels. This is Raman shift. Raman shift. Okay, very good. Now we have scattered radiation, which is having energy less than the excitation energy, that is Stokes lines. We have the scattered radiation which is having more energy than the excitation energy, anti-Stokes lines, anti-Stokes lines, and in addition to these two, we have also same frequency means excitation frequency and scattered frequency same. That means in the scattered radiation we have three components. One component is having the same energy, incident energy is same as scattered energy. Okay, that is invented by another scientist, not Raman. That the scientist name is, you can have a look here. What is this? Rayleigh. It is another scientist. Incident radiation and scattered radiation is having same energy. That is Rayleigh scattering. Rayleigh scattering. Okay. So here we have Stokes lines, anti-Stokes lines. You can have a look here. Let me maximize this one here. We have Stokes lines here and anti-Stokes lines here. And this is Rayleigh. So these are having, Stokes lines are having lower energy, anti-Stokes lines are having higher energy, and Rayleigh is having same energy. Same energy. That's why we usually say that this Rayleigh is due to elastic collision. Elastic, it is not writing, I am writing now. It is due to elastic collision. Okay. This one Rayleigh is due to elastic collision. Elastic collision means incident energy and scattered energy is having same energy of the radiation. Okay. That is elastic collision. Inelastic collision. Now Stokes and anti-Stokes, these two together is due to inelastic collision. Stokes and anti-Stokes lines are due to inelastic collision. Why? What is meant by inelastic collision? In inelastic collision, during collision between radiation and the molecule, energy may transfer either from radiation to molecule or molecule to radiation. Okay. Some of the energy may be transferred from radiation to molecule or molecule to radiation. Now tell me, which one is from radiation to molecule? Which one is from radiation to molecule? Tell me. It is Stokes. It is Stokes. In the Stokes Raman scattering, the radiation is transferred from, energy is transferred from radiation to molecule. Radiation to molecule. Okay. In anti-Stokes, energy is transferred from molecule to radiation. That's why in the anti-Stokes, scattered radiation is having higher energy than incident energy. Are you getting point? So that means some of the energy is transferred from molecule to radiation. Did you get the point? So these two, Stokes and anti-Stokes, together called as inelastic collisions. Now you can see here I kept a simple diagram here. This is E nu Ex. Nu Ex. That means excited radiant frequency, and here we are having the Rayleigh line. This is Rayleigh line. Okay. This is low energy Stokes line. That means this is the shift. This is the shift. Okay. We can say that is Raman shift. You can see mu Ex minus mu V. Mu Ex minus mu V. Okay. And this one mu Ex plus mu V. This is minus, this is plus. Raman shift. Raman shift. This difference depends on what? This shift depends on what? The difference in the vibrational energies. Vibrational energies. V is equal to 0 up to V is equal to 1. This difference. This shift depends on the difference in vibrational energies. So now you can see here. This is Rayleigh. Actually, this is Raman spectrum of CCl4, carbon tetrachloride. Raman spectrum of carbon tetrachloride. Okay. And here you are seeing three peaks. Negative 218, positive 218. Negative 314, positive 314. Negative 459, positive 459. Did you observe? Huh? It is the same value. How much a particular peak, how much it is shifted from rally line to the left side, it is the same from rally line to right side. Okay? You see? 280, 280, 340, 314, 459, 459. That means the information what we are getting from Stokes part of the spectrum is same as anti-Stokes part of the spectrum. That's why most of the time we prefer to record only Stokes lines. Only Stokes lines. That means in the Raman spectrum, what we are recording is only Stokes lines. Now you may have a doubt, sir, why we are preferring Stokes? Why can't we prefer anti-Stokes? Because the Stokes lines are having more intense compared to anti-Stokes. Now again you may have the doubt. Why? Why Stokes lines are having more intense compared to anti-Stokes? Most of the time the molecule will stay in V is equal to 0. V is equal to 0. You can see here. It is started from V is equal to 0. In the case of anti-Stokes, it is started from V is equal to 1. So the probability of a molecule to stay at V is equal to 0 is more than the probability of a molecule to stay at V is equal to N. V is equal to 1. Because of the probability, V is equal to 0 is more probable. That's why Stokes lines are more intense. More intense. Intensity of any line in any spectrum depends upon probability of transition. Probability of transition. If a particular transition is more probable means it will give more intense peaks in the spectrum. Whatever may be the spectrum. Okay? Here also it is the same. That means in the Raman spectrum, now onwards we will see only Stokes part of the spectrum. Okay? So this is I already explained the same actually. Is it stopped? How can I pause? Okay, let it go on. Just I will come back. I will edit, no problem. Okay. So it is explaining the same thing actually, what I already explained. Here it is showing all the transitions together in the same diagram. You can see these are the ground electron state in which there are vibrational levels. These are vibrational levels. So V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 3 and so on. Okay. This is what? Lowest excited electron state. V is equal to 0, V is equal to 1, V is equal to 2 and so on. And this is J, J is equal to 0, J is equal to 1. These are virtual states. Virtual states, you can see here. And here there is thick line, heavy arrows. You can see these are heavy arrows. For example, the electron transition is taking place from V is equal to 0 to J is equal to 0. And while coming back, it is coming back to the same state. That means J is equal to 0 to V is equal to 0. The starting point, ending point is the same. That will give you Rayleigh lines. Rayleigh lines. You can see here, Rayleigh scattering. The excited frequency and scatter frequency same. Elastic collision. Elastic collision. Okay. Now let us consider transition from V is equal to 0 to J is equal to 0. But while coming back, J is equal to 0 to V is equal to 1. Starting point is 0, ending point is 1. Okay. This is delta E. This is delta E, which is nothing but frequency shift. Frequency shift or energy shift or frequency shift. As we know very well, energy is directly proportional to frequency. Okay. Right. This is Stokes line. This is giving Stokes line. Stokes line. And anti-Stokes lines, starting point is V is equal to 1, going to J is equal to 1. And while coming back, J is equal to 1 to V is equal to 0. The scattered radiation energy is having more energy than excitation energy. Okay. So I already explained about this. Now I am coming to wave model of Raman and Rayleigh scattering. Wave model. Actually, the main difference between IR and Raman you will understand from wave model. Wave model of Raman and Rayleigh scattering. Let me explain to you here. Here this is a derivation. Wave model is a derivation. I am deriving now. And from this wave model you will be able to understand the difference between IR and Raman. Okay. Now wave model of Raman scattering. Let us consider this is molecule and a radiation incident on it. When the radiation incident on it, the molecule will interact with electrical component of the radiation, because radiation is electromagnetic radiation. It will have both two components, electrical component and magnetic component. Let us consider the electrical component is interacting with the molecule, and that electrical component E is equal to E naught cos 2 pi nu ext. This is waveform. This is the waveform of electrical component. Okay. E is equal to E naught cos 2 pi nu ext. Okay. Now, when the electrical component is interacting with the molecule, it will start disturbing. It will start disturbing bonds in the molecule. That disturbing is also can be called as M. Okay. M is nothing but induced dipole moment. Induced dipole moment. Induced dipole moment, something which is forcefully happening. It is induced. It is not there, but it is induced. It is induced due to what? Electrical component of the radiation. M is directly proportional to E. M is directly proportional to E. The induced dipole moment, M is directly proportional to the magnitude of electrical component present in the radiation. Is it clear up to here, this point? Okay. Now I will introduce a constant. I will introduce a constant, and name of that constant is called as polarizability. Name of that constant is called as polarizability. M is equal to alpha E. Alpha E. And this alpha is nothing but polarizability. Polarizability. This concept is very important in Raman spectrum. In Raman spectroscopy, this concept of polarizability. What is meant by polarizability? Polarization. What is meant by polarization? Polarization means forming charges, forming poles. Poles means charges. But polarize means polarize something. When we are saying polarize, that means forming charges. Okay? Charges are nothing but poles. Charges are nothing but poles. Polarizability means ability of a bond to polarize. Ability of a bond to polarize. Okay? For example, if these are the two atoms and these are vibrating. These are vibrating. Let us consider both the atoms are same. This is hydrogen, this is also hydrogen, and there is a bond between. There is a bond between these two, and we know that no molecule is under rest. Every molecule, all the atoms are under vibration. Even if you take the molecule to absolute zero. Okay? So these vibrations are common. This is natural phenomenon. And on this molecule, the radiation incident on it. So when the radiation incident on it, the polarizability, when the bond length is increasing, polarizability increasing. Okay? Ability to polarize is increasing. Okay? Induced dipole moment is increasing. Okay? When the atoms are coming closer, bond length decreasing. Bond length decreasing means ability to polarize decreasing. Ability to polarize is decreasing. Obviously, induced dipole moment also decreasing. Okay? So, Raman scattering is mainly due to polarizability. And polarizability depends on polarizability alpha is equal to alpha naught plus R minus REQ times dou alpha by dou R. This polarizability alpha, this is alpha naught. Alpha naught is nothing but now let me explain to you. This is a vibration. This is vibration. Okay? This highest length, this is lowest length. In between there is equilibrium distance between two atoms. Alpha naught is polarizability at equilibrium internuclear distance. This is equilibrium internuclear distance. And this is alpha naught is a polarizability. It is a polarizability at REQ. And what about R? It is internuclear distance at any point. At any point. And dou alpha by dou r means, what is meant by dou alpha by dou r? It is change in polarizability with respect to change in internuclear distance. Change in polarizability with respect to change in internuclear distance. That is dou alpha by dou r. Now, this r minus req is equal to let me you can see here r minus req is equal to rm cos 2 pi nu bt. Okay, so rm cos 2 pi nu bt. What is this rm? Rm is nothing but maximum internuclear distance. Maximum internuclear. When it is vibrating, this is the maximum point, this is minimum point. In between equilibrium. Okay? Rm is maximum internuclear distance. And that means the difference between r minus req, that means the difference between these two depends on the maximum internuclear distance and the vibrational frequency. Rm is equal to cos 2 pi nu bt. Okay, let us consider this is equation 1, this is equation 2. Substitute equation 2 in equation 1. That means alpha is equal to alpha naught plus alpha naught plus rm cos 2 pi nu v t dou alpha by dou r. Let us consider this is equation 3. Substitute equation 3 in equation of induced dipole moment. That is equal to m is equal to alpha e. So we need to substitute this one here. So that means m is equal to alpha means alpha naught plus rm cos 2 pi nu v t dou alpha by dou r. Alpha part completed. And what about e? Already we know e is equal to e naught cos 2 pi nu ext. Okay, so e naught cos 2 pi nu ext. Okay, this is nu v, this is nu ex. Nu ex means excitation frequency. Nu v means the frequency corresponding to vibrational energy level difference. That means difference between v is equal to 1 and v is equal to 0. Okay, vibrational energy difference. Now multiply this expression with this one. Okay, right. m is equal to alpha naught e naught cos 2 pi nu ext plus Rn e naught dou alpha by dou r cos 2 pi nu ext times cos 2 pi nu vt. Is it clear up to this point? Just I multiplied. Okay. So cos 2 pi nu ext times cos 2 pi nu vt is equal to. So here I am using some trigonometric equation, a formula. For example, if you have cos x times cos y, cos x times cos y, cos x plus y plus cos x minus y divided by 2 cos x plus y plus cos x minus y divided by 2. This is cos x times cos y formula. Okay, according to this formula, this is similar to this. In the place of x we have 2 pi nu ext. In the place of y we have 2 pi nu vt. Okay, now I am applying this formula. Cos here 2 pi t is common. It is common. I am taking that one as common. Cos 2 pi nu ex plus nu v t plus cos 2 pi nu ex minus nu v t. Okay, cos 2 pi nu ex plus nu v t plus cos 2 pi nu ex minus nu v t. Is it clear? So if it is clear, I am going to substitute this one in the main expression. What is that? M is equal to alpha naught e naught cos 2 pi nu ext plus, okay, now Rn e naught dou alpha by dou r. Now I am putting also divided by 2. Here there is divided by 2 also. Okay, divided by 2. Okay, and that 2 I am keeping here. After keeping that one, cos 2 pi nu ex plus nu v t plus Rn e naught by 2 dou alpha by dou r cos 2 pi nu ex minus nu v t. Okay, so now we have 3 terms. This is term 1, This is term 2. This is term 3. There are 3 terms. 3 terms. Now the first term. What is the frequency of first term? Excitation energy is same as this induced. What is this one? This is induced dipole moment, isn't it? Induced dipole moment is split into 3 components. 3 components. And first component is represented by term 1. Second component is represented by term 2. Third component is represented by term 3. Okay? Now, the first component, alpha naught E naught cos 2 pi mu ext, it is representing Rayleigh line. Rayleigh line. That means scattered radiation is having same energy as that of incident radiation. That's what you are seeing, Ex. Okay? And here, the second term, Rm E naught by 2, dou alpha by dou r, cos 2 pi mu Ex plus mu v. Mu Ex plus mu v, that is something added to the excitation energy. That means it is term 2 is representing anti-Stokes lines. Term 2 representing anti-Stokes lines. Okay? Because the scattered radiation is having higher energy or higher frequency than the incident one. That means it is adding, mu v is added to mu Ex. This is anti-Stokes lines. And the term 3 indicates Stokes lines. Stokes lines. Okay? So this way, in this wave model, we have three components which we are seeing in Raman spectrum. Rayleigh line, anti-Stokes line, and Stokes line. And here, remember, this dou alpha by dou r is very important component. That is not here in the first term. In the first term, do you have dou alpha by dou r? No. In the second term, we have dou alpha by dou r. Third term also dou alpha by dou r. What is dou alpha by dou r? Change in polarizability. Change in polarizability with respect to change in internuclear distance. That is very, very important. Okay? So, there is a selection rule now. Selection rule. According to selection rule, dou alpha by dou r must be greater than 0. Must be greater than 0. The change in polarizability with respect to change in internuclear distance must be greater than 0. That is the condition. That is the condition. Now you may have doubt. What will happen if dou alpha by dou r is equal to 0? Huh? If it becomes 0, term 2 becomes 0, term 3 becomes 0. In that case, m is equal to alpha naught E naught cos 2 pi mu ext. You will be remaining with only one term, that is first term. That means you will have only Rayleigh line, no Raman scattering. If dou alpha by dou r is equal to 0, no Raman scattering. No Raman scattering. You will get only Rayleigh scattering. Okay? And second one is the change in vibration level must be either plus or minus 1, plus or minus 2. That's it. Change in vibration levels must be a plus or minus 1 or plus or minus 2. These two are called as selection rules. Selection rules. Let me show you that one here. You see? There must be change in polarizability, dou alpha by dou r, which must be greater than 0. Raman lines corresponding to fundamental modes of vibration occur with delta E is equal to plus or minus 1, just as with IR spectroscopy. IR spectroscopy. Okay? That's why Raman spectrum and IR spectrum, both of them are depending on vibrational frequencies. Vibrational frequencies, vibrational energy levels. Vibrational energy levels. The information what we are getting from Raman spectrum and IR spectrum is the same. But the problem is here, some of the bonds which are IR inactive are Raman active. Some of the bonds which are Raman inactive are IR active. Okay? That is the advantage for us. Now difference between Raman and IR spectrum I am showing you now. On the same graph I am showing you difference between Raman and IR spectrum. Now have a look. Let me maximize one. This is a same spectrum, same graph showing two spectra. Same graph showing two spectra of this compound. What is this one? Mesitylene. The name of this compound is mesitylene. This is benzene, CH3, CH3, CH3. This is mesitylene. And here Raman intensity, IR transition. Okay? In the IR spectrum, let me show you IR spectrum generally. IR spectrum usually will be like this. So usually this is a percentage transmission. Okay? On this one, this is centimeter inverse. Centimeter inverse. Actually, it is a wave number. Wave number, but we are saying IR frequencies. IR frequencies. That means usually it is 400. This is 4000. Usually IR spectrum ranging from 400 to 4000 centimeter inverse. Centimeter inverse. And the spectrum will be always like this. Something like this. We are getting inverted peaks. Inverted peaks. These inverted peaks indicates the absorption of energy, radiant energy. That means at this particular point, radiation absorbed. Radiation absorbed. This peak indicates radiation absorbed. And this transmission, it is 100%. This is 100%. That means here, for example, at this point, there is no any peak. There is no any peak. At this point, there is no any peak. That means 100% transmission. No, 100% transmission means zero absorption. Zero absorption. Are you getting the point? 100% transmission means zero absorption. And when it is coming down, transmission is reducing. For example, here it is 50%, let us consider. 50% means 50% absorbed, 50% transmitted. So, inverted peaks indicates absorption peaks. Absorption peaks. Let me show you here. You can see these are the inverted peaks. This is IR spectrum. I am coming here down, down, down. You can see this is IR spectrum. Okay? Raman spectrum. We are seeing upward peaks because here this is emission spectrum. We are recording emitted light. Emitted means here actually scattered frequencies. Scattered frequencies means which is coming from the molecule. Are you getting it? When the radiation is sent on it, we are recording scattered frequencies. That means it is emission spectrum. Simply speaking, in Raman we are recording absorptions. In IR we are recording absorptions. In Raman we are recording emissions. Raman is a emission spectrum, IR is a absorption spectrum. Okay? Now you can see here the peaks are upward because these are emission. You can see here. upward peaks. Now by observing these two spectra, what is your observation? By looking at these two spectrons, what is your observation? For this peak, you have this peak. There are common peaks. For this peak, we have this peak. For this peak, we have this peak. For this peak, we have this peak. Okay? So that means there are common peaks appeared in IR spectrum and Raman spectrum. Those are due to the bonds which are both IR active and Raman active. Both IR active, Raman active. Those are giving peaks in both the spectra. Okay? Now, if you observe this peak, is there any peak here? At this point? No peak. Here there is no peak corresponding to this. Even for these two, is there any peak here? Because these are very sharp peaks, very strong and sharp peaks. And here there is no peak in the Raman spectrum. That means the bonds which are giving these two peaks are Raman active, but IR active, but Raman inactive. Did you get the point? IR active, but Raman inactive. Now I am going to see opposite direction. Okay, for this peak. Okay, if you consider this peak, this is a strong Raman peak. Even this one is a strong Raman peak, and there is no peak at IR. See, this is strong Raman peak, but there is no peak at IR. Okay, so some of the bonds are Raman active, but IR inactive. Okay. Now, if you see the difference, there are common peaks which are both Raman active and IR active. There are certain peaks which are present in IR but not present in Raman. There are certain peaks which are present in Raman but absent in IR. Okay? That means there are certain vibrations, there are certain bonds which are IR active but Raman inactive. Okay? That means you can see those peaks in IR spectrum but absent in Raman. Okay? There are certain peaks which are Raman active but IR inactive. You can see for those you have Raman peaks but there is no peak, there is no corresponding peak in IR. Okay? Simple logic, Raman frequency shift is equal to IR vibrational frequency. Right? IR vibrational frequency. That's why we are representing same spectrum. We are representing two different spectrum on the same scale. But this scale, in the case of IR, it is vibrational frequency directly. Whereas in Raman, it is frequency shifted. This one. And this is, remember, this is Stokes part of the Raman spectrum. We have Rayleigh. This is Rayleigh actually. See, from the Rayleigh we are collecting only Stokes part of the spectrum. Actually, in Raman spectrum we have other part. The same. You can see other part here. It will be an anti-Stokes part of the Raman spectrum. But we need only one part. Only Stokes part will be enough. And you can see also here, this is another example. This is for Indian. These are common peaks. This is common peak, common. So, for example, this one, IR active, but Raman inactive. Okay. For example, let me pick one. inactive. Most of the Raman peaks are also seen in IR spectrum. Okay. So this is all about the difference between Raman and IR spectrum. Okay. Now we are coming to another one. Intensity of normal Raman bands. Okay. Intensity of Raman bands depends on different factors. Number one, nature of the molecule. The polarizability nature of the molecule. That is one. Okay. And intensity of the incident light. Intensity of the incident light. Okay. If the intensity of incident light increases, Raman scatter line's intensity also increases. Okay. But if you keep these two constant, that means for a molecule, always polarizability is fixed. Okay. For a given molecule, polarizability is fixed. It is its nature. It is fixed for a given molecule. And when you fix the intensity of light, and we need high intensity. Here, in order to get Raman scattering light, we need very high intensity, and that higher intensity will present only in this radiation. What is this? Laser. That means in Raman spectroscopy we are using laser. Which region? We are using UV, visible, near IR. UV, visible and near IR ranges of laser radiation we are using, because intensity, we need very high intensity in order to get Raman scatter lines. Okay. So, and when we fix this intensity, laser intensity, if we fix constant, then Raman intensity is directly proportional to concentration. Raman scattered radiation intensity. Raman scattered radiant intensity is directly proportional to concentration, provided the intensity of incident light must be kept constant. Okay? Right. Raman intensities are directly proportional to the concentration of active species. This is the principle for quantification. That means Raman spectroscopy can be used for both qualitative as well as quantitative analysis. Okay? Right. And we have another parameter. In the Raman spectroscopy, we have another parameter called as Raman depolarization ratio. Raman depolarization ratio. Raman depolarization ratio, P is equal to I parallel divided by I perpendicular. Now let me show you. Let me explain this one by using this image. Okay. Before looking at this image, I have to give you some concept. Plane polarized light. Do you have any idea about plane polarized light? When you are seeing this light, the light which is coming from this one, it will be having oscillations in all the planes. It will be having oscillations in all the planes. The wave, for example, a wave may be like this, another wave may be like this, another wave may be like this, in different angles. That is called as non-polarized light. Okay. When you pass this non-polarized light through a device called as Nichols prism. What is that? Actually, this is very popular in physics. Nichols prism. Nichols prism. When you pass this radiation, non-polarized light through Nichols prism, what it will do? It will cancel all the planes and keep only one plane. One plane. That is called as plane polarized light. Plane polarized light. When you pass non-polarized light through a Nichols prism, it will make plane polarized light. When you allow this plane polarized light, you can see polarized radiation. This is plane polarized light. It is coming and instantaneous. Okay? When it is instantaneous sample, this is sample. When this plane polarized light, let us consider this is xz plane. The plane of this plane polarized light is xz. Okay? And after instant on this, you will be having a wave in this direction. This is yz. Okay? This is xz, this is yz. And these are parallel to each other. This is, I can say this is called as, of course this is scattered radiation. This is incident radiation, this is scattered radiation. This scattered radiation wave, this wave is parallel to this wave. Okay? That means this is parallelly polarized scattered radiation. Parallelly polarized scattered radiation. Now I am coming to this one. This one I can say this is in xy plane. XY plane. And this one is like, see for example, this is like this. This is like this. Okay? This one my right hand. Okay? This one is my left hand. This one is this black one. Okay? Are you able to get it? This is how. This is perpendicularly polarized. So there is a parameter called depolarization ratio. What is depolarization ratio? This is called depolarization ratio. P is equal to intensity of parallelly polarized light divided by intensity of perpendicularly polarized light. The ratio of intensity of parallelly polarized light to perpendicularly polarized light is called as depolarization ratio. Okay? What is the advantage of this parameter depolarization ratio? Okay? The advantage of this depolarization ratio is to know the mode of vibration. Whether a particular vibration is symmetric vibration or unsymmetrical vibration. We know that vibrations are two types: symmetrical vibrations and asymmetrical or unsymmetrical vibrations. Symmetrical, asymmetrical. If vibration is symmetrical vibration, for example, if you consider this one, this 459, the peak at 459. When you calculate depolarization ratio for this peak, it is a P is equal to 0.05. 0.05. Okay. When you calculate depolarization ratio for this one, 0.75. 0.75. So this is very low value, this is very high value. The P value for these peaks is 0.75. P value for this peak is 0.04. This is very low. Low P value indicates symmetric stretching vibrations. Symmetric stretching vibration. Higher value of P indicates asymmetric stretching vibrations. Symmetric stretching vibrations, asymmetric stretching vibrations. Now, if you consider CO2, carbon dioxide, if you consider carbon dioxide, it is a linear molecule, you know. Linear and symmetric. Linear and symmetric, this you can see here, this is carbon dioxide. In carbon dioxide we have different modes of vibrations. Symmetric stretching, for example, let us consider, this is at the center, this is carbon, this is oxygen, this is oxygen. At the center carbon, this is oxygen, this is oxygen. Symmetric vibration means both of them going away, both of them coming closer to the carbon. These two are oxygens. These two are oxygens. At the center, carbon. Both of them going away at the same time, coming closer at the same time towards the carbon, central carbon. So that is called symmetric stretching. For symmetric stretching, P value will be very low. Now tell me whether this symmetric stretching, IR active or IR inactive. Tell me. Symmetric stretching. Symmetric stretching is IR inactive. Okay? But Raman active. Okay? And for example, if you consider asymmetric stretching means at the center there is carbon, these two are oxygens, they will be moving like this. That means when one bond is elongated, other bond is compressed. When one bond length is increasing, other bond length is decreasing. When this bond length is decreasing, this bond length is increasing. They are moving like this. In the previous case, symmetric. Second case, asymmetric. Okay? In the case of asymmetric, it is IR active, but Raman inactive. Okay? This is called as mutual exclusion principle. Mutual exclusion principle. What is meant by mutual exclusion principle? The modes of vibration which are IR inactive are Raman active. The modes of vibration which are Raman inactive are IR active. Okay? This is called as mutual exclusion principle. like 0.05, very low, because it is symmetric mode of vibration. Simple logic. If the p value is very less, it will start like 0.0 something. Okay. The peak is due to symmetric mode of vibration. Okay. If the p value is something like 0.7, 0.8, something like that. Okay. After 0 point, without 0. Okay. 0 point some value. Okay. Then the particular peak is due to asymmetric mode of vibration. So the p value can be calculated practically, and from the p value we can say that a particular mode of vibration due to either symmetric or asymmetric. That is the advantage of the Raman depolarization ratio. So, is it clear? Now I am coming to, with this we are done for all the theory and background of Raman. Now I am coming to instrumentation. Yes. If you see the instrumentation, the parts are very few parts. Have a look. What is the source of light? Laser source. What is the advantage of laser? Intensity. It will have very high intensity. For example, if you see, this is very small pointer. You can see the back side. Huh? Even it can travel half kilometer with the same intensity. Very sharp, pinpointed with high intensity. That is the specialty of laser, because the laser, what is the full form of laser? Light amplification by stimulated emission of radiation. Laser. LASER. Light. L for light, A for amplification. Light amplification by stimulated, S for stimulated, E for emission, R for radiation. Light amplification by stimulated emission of radiation. That is laser. That's why we are getting very sharp radiation with high intensity. Because of stimulation, light is amplified. Now, if you see the parts, there is laser source, there is sample cell. After sample cell, you have wavelength, selector for the selection of wavelength, radiation transducer. It may be photovoltaic tube, but in Raman we have more advanced detectors. Radiation transducer is nothing but radiation detector. It is another name. Radiation transducer or radiation detector is the same. And then computer data system. You can say this one as readout. It is readout. Okay, but in Raman, computer is compulsory. There is no Raman instrument without computer. Number one. Number two, there is no Raman instrument without laser. That's why actually Raman scattering invented in 1930. But Raman spectrometer, the instrument, Raman spectrometer invented after 1960. Why? Laser invented in 1960. That means 30 years. Even though we know about Raman scattering, we failed to design Raman spectrometer instrument. Because of absence of laser. Okay. So the successful instrumentation of Raman is mainly due to availability of laser. If no laser, no Raman spectrometer instrument. So these are the parts: laser source, sample cell, wavelength selector, radiation transducer, and computer data system. Now I am going to explain to you one after another these parts. First, let us start with the laser sources. Okay. There are different laser sources. You can see. Why it is not changing? Okay. Yeah. This is laser source. You can have a look. There are different laser types having a different wavelengths. Argon ion laser, krypton ion laser, helium neon laser, diode, and we have neodymium, yttrium aluminum garnite, YAG. YAG means yttrium aluminum garnite. So these are different types of lasers, and these are having different wavelengths. 488, 514. That means this is visible region, and these two are in near IR. This is visible. This is near IR. Okay. So we are having different lasers in visible region and near IR region. Low wavelength means high energy. Remember, low wavelength means high energy. High wavelength means low energy. So we have high energetic radiation, low energetic laser radiation. We can use according to requirement. But if you use visible radiation, we have an advantage. We can use all the components of the instrument. We can use glass or plastic, no problem. The window materials, optical components like mirrors, lenses, window materials, you can use glass. That is the advantage if you use visible region. But in the IR spectroscopy, all the materials, all the optical components must be made with ionic compounds. Usually NaCl crystal or KBr crystal. Ionic. But here glass is okay. The advantage with glass is the instrument components are a bit strong compared to IR. And another advantage of using visible light is you can use water as a solvent, no problem. But in IR, water should not be a solvent. In IR region, water should not be used as a solvent. So these are the two benefits of using visible laser radiation. What are the two benefits? You can use glass as a component of the instrument, and number two, you can use water as a solvent, because water is universal solvent, freely, easily available. That is also another advantage. Okay. Now we are coming to sample illumination system. Sample holders, the second part. Sample can be glass sample, liquid sample, or solid sample, no problem. Any type of sample can be used. The type of the sample can be gas, liquid, solid. All the three states. We can use all the three states. Whatever the state is available, you can use. But grinding is needed. If it is solid, grinding is needed. Okay. Now I am coming to gas samples. A small capillary tube can be used as a sample container. You can see here. This is a capillary tube and it is holded by this one, and this is small capillary tube. You can have a look here. What is this one? This is source. From the source, the laser source, from the laser source, the radiation is coming here. This is the lens. You can use glass as a lens. Now you can see here. Sorry. Laser beam is here. Laser beam is here. This is incident radiation. Incident radiation. This is scattered radiation. Scattered radiation. After this, there will be a monochromator and detector. Monochromator and detector. Okay. Now I am coming to liquid samples. Liquid sample also can be placed in a very narrow capillary tube like this. Laser beam incident, and this is scattered. This is scattered. After this, there will be wavelength selector and radiation detector. We can use the same. Here in the capillary tube, gas. Here in the capillary tube, liquid. And we can use also a cylindrical type, a bit wider cylindrical type of tube for liquid sample. It is possible. But when you are using like this must be rotated. This must be rotated in order to avoid local heating. Okay. This is for liquid sample. Liquid sample can be placed in this holder. Now we are coming to solid samples. You can see here solid sample. Actually, solid sample must be grinded, and while grinding, you need to add little bit KBr as a background material to keep the sample molecules in KBr in order to get a good Raman spectrum. You can see here. Sample in KBr, and there is a KBr holder, potassium bromide. Okay. So fine particles of sample must be dispersed in a matrix KBr. So that's how it works. And now I am coming to third part, wavelength selector. Usually, wavelength selector in the beginning, when we developed Raman spectrometer, we were using double or triple grating system. In the beginning, we were using double or triple grating system, but later on, we developed another type of, because in this case we need high resolution, very high resolution wavelength selector. Very high resolution wavelength selector is needed. Okay. For that matter, we have advanced wavelength selectors called as holographic interference filters. These are also called as notch filters. And we have holographic gratings. Holographic interference filters called notch filters, and holographic gratings are the ones what we are using as wavelength selectors in this instrument. We can use normal grating wavelength selector or prism wavelength selector, but it must be multiplied 2 or 3 times. But if you are using this one will be enough. Notch filters or holographic grating. Okay. So this is wavelength selector. Now I am coming to radiation transducers or detectors. We know very well from chapter 2 that photomultiplier tube is a best detector. Of course, that is best detector for atomic absorption, atomic emission, atomic fluorescence, okay, and UV visible spectrophotometer, okay. But when it comes to this Raman spectrometer, we need more advanced, more efficient, more advanced and more efficient detectors. Those are photodiode array detectors. CCDs. CCDs means charge coupled devices. Charge coupled devices. CIDs. Charge injection devices. And we have cooled germanium detector. These are all advanced detectors. Advanced detectors than photomultiplier tube. Photomultiplier tube. Photodiode array detector. CCD, charge coupled detector and charge injection detectors. We have cooled germanium detector. These are more advanced detectors. These are needed. Among all, this one is the best one. Cooled germanium detector. Detection process is mainly depends on the creation of holes and electrons, because germanium is a semiconductor. Okay, yeah. Right. We are coming to the complete instrument. Complete instrument in which the major parts are only 4. What are the 4 parts? Number 1, radiation source. Number 2, sample container, sample holder. Number 3, wavelength selector. Number 4, radiation detector, and finally display will be there computing. And when we are saying FT, this is also called FT. FT Raman. It is similar to FT-IR. FT-IR. FT-IR, FT Raman. FT-IR and FT Raman. Actually, functioning of FT-IR and FT Raman is very same, very similar. Functioning is very similar. See, we have FT-IR, we have FT Raman, we have FT Yanama. What is this FT? FT-IR, FT-IR instrument, FT Raman instrument, FT Yanama instrument. FT is Fourier transformation. Fourier transformation. Now I am going to ask you, what are these things? What are these things? Yes, these are nothing but mathematical operators. Mathematical operators. Plus, minus, into, divided by, d by dx, integral. Mathematical operators. This is for addition. This is for subtraction, multiplication, division, derivative and integration. Okay, these are called mathematical operators. Similar to this is the advanced mathematical operator. FT is advanced mathematical operator which can be performed only by computer. We cannot do it. That Fourier transformation is an advanced technology which can be done only by computer. Without computer we cannot do it. Okay? Okay. So what it will do? The Fourier transformation. So you will be having a complex signal. For example, let us consider there are many waves here. Many waves. Okay? This Fourier, this one we can say as interferogram. Fe. What is the interferogram? Interferogram is nothing but it is a single beam having many waves. All the waves, in fact. All the waves as a single signal. That is called as interferogram. Interferogram is a single signal having many waves, bunch of waves together is called as interferogram. Okay? So this will FT is work based on interferogram. First it will make interferogram. From the interferogram, the Fourier transformation is a computation technique which will convert this interferogram into normal spectrum. First it will develop interferogram. Interferogram is itself is a spectrum. It is itself is a spectrum having all the wavelengths, right? But those can be converted to normal spectrum by Fourier transformation. Now let me show it here. It's very bit. You are looking a bit complex, but when I explain, it will be easy for you. Okay? When you are seeing, oh, it's very difficult, but it will be easy. Now you can see this one. This is the source, radiation source. Neodymium, yttrium, aluminum, garnet, laser with line filter. Okay? Now this one, from this one radiation is coming out, and here there is a mirror to reflect, and here this is lens to focus. Okay? After focusing, this is the sample. Where it is focused? It is focused on the sample. So the first part, second part completed. Source of radiation, and this is sample. In between there is mirror and lens. Of course, small optical components must be used as per the requirement. The purpose of this mirror is to reflect. The purpose of this lens is to focus. Where it is focused? Focused on the sample. After focusing, we know what will happen. There will be elastic collision, inelastic collision. There will be Rayleigh lines. We have Stokes lines and anti-Stokes lines, and all these are together. And here it will make a single signal called as, you can see here, it is invented by you can see here, what is the name here? Michelson interferometer. The purpose of this Michelson interferometer is to generate interferogram. In order to generate interferogram, you can have a look here. In order to generate an interferogram, there will be a fixed mirror here and there is a moving mirror here. This is semi-transparent mirror, which we can say this is a beam splitter. Beam splitter. This beam splitter is a semi-transparent mirror. That means some of the radiation will be reflected to fixed mirror, some of the radiation is passing through the mirror towards moving mirror. There will be fixed mirror and moving mirror. Okay? This arrangement is to generate interferogram. And this interferogram is passed through a mirror which is reflected, and here it again passes through another mirror to incident on a concave mirror, and here this is spatial filter. This is wavelength selector. Spatial filter, which we say notch filters. Notch filters, holographic interference filters or holographic gratings. Okay, this is nothing but wavelength selector. So after wavelength selector, now this radiation is allowed to go to the detector. What is this one? Liquid nitrogen cooled germanium detector. This is a germanium detector which must be cooled by liquid nitrogen. In order to protect the detector, there must be cooling system. So liquid nitrogen cooled germanium detector. So which will detect the radiation, and then it will be converted into Raman spectrum by what? By computer. Without computer, no FT Raman. And we are getting enough intensity of Raman signals with only FT instrument. Okay? This is all about FT Raman spectrometer. Is there any doubt? If no doubt, we are moving on to applications. The last part of Raman spectroscopy, that is applications of Raman spectroscopy. Raman spectroscopy is very useful for inorganic species. IR spectroscopy is highly useful for organic, but IR spectroscopy can be used for both inorganic as well as organic. Why inorganic? Most of the inorganic systems are soluble in water. But in IR we should not use water. Here we can use water. There is no problem. Okay? So, because you can use water as a solvent, and Raman can be used for the study of Raman spectrum of inorganic species. Spectra of such species like VO3 4 minus, ALOH 4 times minus, and these ones have been obtained. In perchloric acid solutions, vanadium 6 appears to be present as VO2 2 plus rather than VOH twice 2 plus, like this. That means the speciation study. We can also do the speciation study by using Raman spectrum. A particular metal ion present in which form? Whether it is in this form or this form. That can be studied by using Raman spectrum. Studies of boric acid solutions show that anions formed by acid dissociation is tetrahedral rather than H2BO3. So that means this boric acid is present in this form rather than in this form. Okay, speciation study. So, and this is also useful for the measurement of dissociation constants. Dissociation constants for strong acids, such as these ones, have been calculated from Raman measurements. It is possible. Okay, and we have Raman spectra useful for organic species, particularly when you have olefinic bonds. Olefinic bonds means, okay, C double bond C. C double bond C is very much symmetrical, okay, or C triple bond C. These kind of bonds you cannot study by using IR, but you can study by using Raman. And cyclic aromatic compounds also you can study more with Raman spectroscopy compared to IR spectroscopy. And one more thing is, Raman spectroscopy can be applied to biological systems. It can be applied to biological systems. Why? Most of the biological systems are soluble in aqueous medium, biological molecules. So because you can see the minimal sensitivity to water. That is one advantage. The spectral detail and the conformation and environmental sensitivity. Because of all these things, we can study biological molecules by using Raman spectrometer. Quantitative. When it comes to quantitative, see for example, because it's laser can be focused on pinpointed, very much pinpointed, okay. Because of that advantage, even you can study a small particle of smoke. A small particle of smoke can also be studied. A small particle of exhaust gas can be studied, because we don't need a huge quantity of sample. The sample quantity can be very small. A fine particle can be studied by using Raman spectrometer. And as we know very well, I is directly proportional to C. Raman intensity is directly proportional to concentration. Higher the Raman intensity, higher the concentration. Because of this relationship, you can measure Raman intensity and calculate concentration. You can get the concentration. You are getting concentration means it can be useful for quantitative applications. Determination of analyze in single bacterial cells. You can see single bacterial cells. Components in individual particles of smoke and fly ash and species in microscopic inclusions in minerals also can be studied by using Raman spectroscopy. This way, Raman spectroscopy is very useful technique. And the information what we are getting from Raman and IR are the same, but Raman has some special advantages of using glasses in the instrumental parts, using water as a solvent. These are the two benefits, because we are working in visible region. Is it okay? And also, all the Raman inactive bonds are active in, all IR inactive bonds are active in Raman. That is also another advantage of Raman spectroscopy. With this, we are done for Raman spectroscopy. Tayari. Okay? Yeah. Now you ask me if you have any doubts. Let me